So continuing on applications, and again, and more specifically with the examples for using friction and the coefficient of friction that we may have for it. When we have, you push a 25 kilogram wooden box across a wooden floor at a constant speed of 1 meter per second, how much force do you exert on the box? What would the acceleration be if the force were doubled? And so I'm just going to resize this here a little bit that we have. So we have that. So we need to look up that, and by looking it up, we got our mu sub k. So that'd be the coefficient of kinetic friction since it's moving at 0.2. Again, remember these do not have labels on them as well. We then have a mass of 25 kilograms. Because it's in kilograms, we're not going to need to convert that into kilograms. We also need to know our gravity, because ultimately the normal force that we use in the equation of the frictional force is equal to mu sub k or mu sub s in a lot of ways. A lot of times we're going to write normal force, and we have to write normal force because it's not always weight. Especially when we start doing things that are on a slope, the normal force is not always the weight, and we'll look at that, I think, in next time. So for today, it's going to be weight, but we can't really, and we're not supposed to say that it's weight. And so we have to be very careful about how we think about these, and it does need to be written as the normal force there. The gravity part of it is always going to really be there. It's just going to be a little bit different, and as we kind of put things at an angle as well. Because it's moving at a constant, the pushing force, or the normal force of it pushing, is going to be equal to the frictional force, and that is going to be then equal to the coefficient of kinetic friction times the normal force, which, or in this case, weight, which is 25 kilograms times 9.81, and that should really start putting in our labels so that we can know what's what there as well. So some cases it is going to be a nice, easy, just kind of multiply things out. So 0.2 times 25 kilograms times 9.81 meters per second squared, and we get a answer of 49.05 newtons, or roughly 49 newtons with that. And now if we doubled the force, so if we're going to double that on us, now we have to, okay, if we're going to double this, and so we'll multiply it by 2, and that's going to equal the mass times acceleration. So if I double the force, 49 times 2, 98 newtons, is equal to the mass, and that hasn't changed, and so that would still be 25 kilograms, times A, divide so that we can get A by itself. And when we divide it by 25 kilograms, we get an acceleration of 9.2 1.2 meters per second squared with that. So when the passing assault shaker at 50 grams sliding across the table with an initial velocity of 1.15 meters per second, if the shaker comes to rest with a constant acceleration in 0.84 meters, what is the coefficient of kinetic friction between the shaker and the table? How much time is required for the shaker to come to rest if the initial speed had been 1.32 with that? And so I'm going to resize this again so we have plenty of room with that. And so writing down again what we have, I think, becomes valuable. If you are having a tough time figuring out, what is this, kind of what's going on, when in doubt, draw it out. And we have a mass of 50 grams, which needs to be converted to kilograms, which can be maybe it will be more useful as we kind of look on another one, but we're going to try to do this one by factoring out our mass so that in case we do have a problem that does not have mass, that we see that being done, but we'll convert it in case we get stuck. We'll have the mass just in case. And so we're dividing by 1,000, which would move the decimal place 3 places to give us 0.05 kilograms. We have an initial velocity for the first problem we're going to look at first of 1.15 meters per second. The final velocity, because it comes to rest, is going to be 0 meters per second. The distance that it travels of 0.840 meters there, and we're asked to solve for what is the mu sub k in this case. By kind of paying attention to some of the things, and that we're going to look at kind of the sum of all the forces, or the F net is going to be equal to, in this case, because there's no other objects working on it, a negative frictional force. And that would be, because if you are pushing on it, it would have a positive and a negative because friction would be working against it. And that will be equal to the mass times the acceleration in the x direction, technically. And or you could also say that, and you can just redistribute this negative here over to rewrite the equation as saying the frictional force is equal to a negative mass times acceleration in the x direction. Okay, but we don't have an acceleration in that yet, and so that's where we're really stuck at. And so again, we would need to look at our equation sheet and find a problem that would have this as our, and that would be acceleration, especially acceleration of the x, and have it as d sub x there, 0, and we would kind of substitute things in so that we can solve for it. I think most high school students prefer to put numbers in as fast as we can than solving everything for their unknowns. I think the more advanced you become in physics, the more that they require you to solve for use variables as much as you can until the very end. That's becomes a thing, and it becomes much more mathematic that way, kind of solving for variables. And I think most high school students don't, or at least that's been my experience. And so I go through and I will punch in the numbers, 0.15 squared will give us, and then I'll move it on to the other side so that it kind of not having that set to 0. I'm going to kind of do two things at once. 2, 5, kind of pull in a full calculator readout, is equal to 2 times AX times 8, 4. I should put out the 0 there. Boop. Meters. When you multiply by 2 is up to you, but ultimately we're doing this at either 1 step or 2 steps to get there. And we have a little bit of that action happening for us. And we end up with a negative, or so a sub x is a negative 0. And again, that should make sense because it's slowing down, kind of evaluating our answer. It's slowing down as it comes to rest, so it would have that there. And so now I have that acceleration. What we then have to deal with, and where we say, and that is kind of where part of this comes in that we have what is what, and we have all this added points. And so we do have a force, and so we need to find that normal force that we have. And that would be or F net, and this is where we kind of factor it out and we utilize the frictional force and the F net to our advantage here. F net is equal to mass times acceleration, which is then just also equal to the mass, and that would be mass in the x, and that would be equal to the frictional force, which again is the mu sub k times the normal force, which again, the normal force also being weight. So I think I miswrote the x up in here. Okay, so I apologize for that. And so the frictional force is mass times acceleration. No, the frictional force is mu sub k. So I might have miswrote that. The frictional force is a negative mu sub k times the normal force. That looks better. And so now I have mass times acceleration in the x is equal to mu sub k times the normal force, and then we know the normal force and the weight are very similar, so that would be mass times gravity. We can then say that mu sub, if I factor out the m and say mu sub k times gravity, like so, I then can divide both sides by m. By doing that, I cancel out my mass, which we're going to take what I have left now and kind of move it up. And taking that and moving it into the empty space, and that I have my negative 0.787 meters per second is equal to my mu sub k times gravity, which we know is actually negative 9.81. And so I'm able to divide both of those, and the labels should cancel out as well. Should be squared there. And so 0.787 divided by 9.81 gives me the mu sub k value of 0.08. Now to finish off the problem, I'll have to do some little erasing here, that so we have some room to solve some problems of the other part of it. And that becomes, the second part is what happens if my initial velocity, and so for the second part, the initial velocity is going to be 1.32 meters per second, and the acceleration is going to still be the acceleration that I have found previously. That's why I didn't want to get rid of that. And so now it becomes a solve for time, and so we are now going to utilize those parts of it. You can solve for time using just the general acceleration equation, where acceleration is equal to v sub f minus v sub I, not equal to v sub I, with that. Divided by t, we'll need to factor that t out, which means we multiply both sides by t. And then we can start adding in and saying that t is equal to, at technically is equal to v sub f, which we know to be 0, minus the initial velocity. If I divide both sides now by a, I would have it set up to just solve for t, putting in my knowns, minus 1.32 divided by my negative acceleration of 0.787. I will have then an answer of 1.68 seconds to finish off my next part of my question.